Okay, so good evening, everyone. So I hope I'm audible. So I can. So if I'm audible, then I think we can start today's session, right? So any one of you can please let me know if I'm audible, right? Okay. So good evening. Good evening. Okay, good. So now, last time we discussed 50 questions roughly. Last time also, but that was from production engineering portion. So today we are going to discuss from the machine design portion. Okay. So let's go ahead and discuss some of the questions from this particular section. So in parallel, you just keep on trying and try to attempt these questions, right? Okay. In case of spur gears, static tooth load as compared to dynamic load should be what, right? So you must have the idea of static and dynamic tooth load in case of design of gears. If you have that idea, then I think you can proceed and you can answer, right? So I hope you may be knowing that, okay, whenever in case of let's say if we take the design of spur gears only, very basic design, then how do we calculate the power. So already that the power is equal to 2 pi n. So depending upon on which particular gear you are talking about, let's say if you are talking about pinion, then torque I need to write for pinion, torque on pinion divided by 60. Let's say if you convert it into second. So now what is this torque value? This torque value is what? This torque value is the tangential tooth load multiplied by the diameter of, in case we are taking for pinion, so radius of the pinion, right? So if you are having a pinion, then obviously we say that tangential tooth load that is acting at the this for pinion. This is what it is. Now this is basically, when we input this value, this PT is basically the static tooth load we are talking about, purely based upon the what? Purely based upon the static considerations, or at the best we can say, or gears rotating at very low speed. So it means this load in any case is always going to act. And when we calculate it, you must have seen that this is the, you must be knowing this relation. So Pn is the that load acting, and we can say this is the PT component, tangential tooth load, and this is the radial tooth load. This is the phi, and we can get it calculated, right? So this is how it is. Now, what is the dynamic tooth load? Dynamic tooth load comes from where? See, we say that this is based upon the assumption that, okay, you're having all the gears profiles are perfectly made, right? There is no inaccuracies in the profile, and let us say there is no inaccuracies in the, that is, alignment is perfect and all those. So let us say if an alignment is not perfect, there are going to be inaccuracies in the tooth profile. At the same time, you can just simply think of, you're going to have the misalignment, smaller, even by a small amount. If we consider all those things, then in addition to it, now point is, in addition to it, this will always be acting. This will always be acting. But in addition to it, small amount of some additional load will also be acting. So it means the net or effective load which is coming on the tooth will always be greater than this load, which is based upon the static considerations. So it means, and I hope you may be knowing, I don't know whether you have remember or not, this effective tooth load we calculate by two factors. Okay, now I am removing, so you must have got the idea. So this, how do we calculate actual or effective tooth load? We calculate by two ways. Either what we do is, we know PT will always be acting. So actual load, this is dynamic load, what he's talking about compared to dynamic load. So in case of spur gear, static tooth load as compared to dynamic load should be, okay. So it means static load should always be what? Static load, now see, have a look over here. So PT divided by what? We divide by a factor called as velocity factor. So purpose of dividing by this is to increase the value. This value should increase, right? So this is always if it is in denominator, it is less than 1. Or we have other way also. What we can do, we can say that, okay, this load will always be acting, but in addition to it, some small or some amount of load will also be acting over there. So it means net effective load will be this much. So in case of spur gear, static tooth load right? So that is PT compared to dynamic load. Now dynamic is combined together. This becomes the dynamic. So this is compared to the dynamic load should be what? It should be less than. It should be less than. So compared to this, it should be less than. So static load to load as compared to the dynamic load. Now dynamic, see, there may be misinterpretation from your side. Dynamic load he's talking about, see, in the running condition. Dynamic that he's talking about is in the running condition. Running condition, what is the load acting on the gear tooth? Not only the part, this separate part. He's not talking about this load only. Right? So in running condition, whatever the load, that is this load. So compared to that, this tangential tooth load will always be less. So you can say this is this one. So there is going to be a little bit in misinterpretation in this case. So you may understand that dynamic load, right? So that then you will be talking about this, but this is not the case. He's talking about the running condition. So this is going to be PT should be, that is a static tooth load should be less than the this effective. Okay, so B is going to be the option. Okay, so I hope you got it. Don't misinterpret the dynamic part. Now let's move on to the next one. The maximum tangential load which the gear tooth can take with pitting failure. Just please go ahead and try to answer. Try to give me some of the answers from your side. I want some of the answers from your side. Okay, so over here, you know, what is this maximum tangential load which the gear can carry, can take without pitting failure? What is the pitting failure? Pitting failure is a wear failure only. There's nothing, you know, we have studied only two types of failure in design of gears. One is the bending failure, beam strength, that we call it as a beam strength, and the other one is what? The other one is this wear strength. Wear strength is what? Wear strength is nothing but there should not be any kind of surface fatigue failure. Pitting mean on the surface of this gear there should not be any kind of pits. Pits mean छोटे छोटे गड्ढे. You call them kind of pits. Surface fatigue failure मतलब chips की form में small material जो removal होता है यहाँ से, that is called as pit. Pit आपको you know already the meaning of pit. Pit is गड्ढा. तो small that depressions that get generated because of the removal of the material. तो उसको हमने नाम दिया wear failure. That this gear tooth, instead of getting bent, it may also wear out on the surface. So if it has wear out, for us it is a failure. So what is the wear strength? Wear strength, what we call as a wear strength? Wear strength is nothing but we say that what is that load that I can apply over here, or you can say when it is getting in contact with another gear tooth over here, then what is that load, maximum tangential load that should act over here, which can be carried by this gear teeth without any surface fatigue failure. मतलब ऐसा क्या लोड है जो मैं यहां अप्लाई करूं so that यहां पर ये गड्ढे क्रिएट ना हो when it is in running condition, right? So those pits don't get generated. That is the meaning of this. So what is that? It is a maximum tangential load. ये beam strength भी tangential load ही है, right? This is also tangential load, but this tangential load is that load which can be carried out without any bending failure, whereas this is the same load, not same load, that means a similar load, similar kind of load, that is also tangential load that I can apply without any surface fatigue failure. We also call it as a pitting failure. तो ये क्या है? This he is talking about the wear strength. तो क्लैरिटी होनी चाहिए आपको कि क्या मतलब है इसका. What is the meaning of beam strength, wear strength? क्या है? Strength means what? This is a force only, right? Maximum force that it can carry. So B is going to be the correct answer. Let's go to the next one. Both the pinion and gears are made, this is not arc, are made up of same material. Then which one of the following decide the design procedure? So very soon, Saurabh, it will be launched, I think, very soon. So you will be informed. You just speak to our executive. I think he'll inform you. So, but very soon it will be over there. Okay, so if both the pinion and this gear are basically are made of same material, so from where do you have to decide? You have to decide based upon, you already know in case of beam strength, when you are talking about the beam strength, right? So when you are talking about beam strength, how do we write the beam strength of the gear? So we say beam strength is what? Pi y bm and sigma allowable, right? This is how we say, or we can say that is small y, right? This is the beam strength, right? Beam strength is nothing but this is the maximum tangential tooth load that you can carry. In last question, I just explained you what is the maximum load that you can carry without bending, right? So over here, which one is the deciding factor? These two and pi, they are going to be same for the this that particular gear and pinion, and both they are made up of same material. If material is also same, allowable value of stress is also going to be same. So deciding factor is Lewis form factor. And for pinion, Lewis form factor, you may be having idea. So they are something kind of 0.684. Sorry, I think I not exactly remember 0.154, 0.17175, and point something or 64 or something this way, and then 0.194 something, minus minus minus, and denominator you are having z values, right? 0.684 something this way. So now you are having this z over there, then there is a number of teeth. So when you will calculate it over there, y is always going to be smaller for the pinion. So it means when y is smaller for the pinion, all other things remaining same, it means the pinion will carry the less load. So the pinion is the weaker, right? Since Lewis form factor is smaller, so pinion is the weaker. Therefore, we will say we have to design it based on. So if pinion is the weaker, we have to make it safe. If we have to make it safe, then obviously we are saying that we have to design our it based upon that. Just see these values. You don't need to remember, but just general idea you need to have if you have to interpret it. He may ask you, see, keep it in mind. He may ask you these values directly also, because this is for 14 and a half and all that. 14 and a half, 20 degree full depth and 20 degree stub depth, something these values, right? Okay. Now let's move on to the, so B is the correct option. So let's move on to the next one. In which condition the pinion is in which condition the pinion is weaker in bending? In which condition pinion is weaker in bending? Again, you have to utilize the same your formula, that is the beam strength, or beam strength is nothing but the maximum value of tangential tooth load that your gear can carry. This is the maximum tangential tooth load that your gear can carry without any bending failure. That is the meaning of FT max, tangential tooth load. PT max you all can also call it. So again, pi ybm. So what is that? So ybm into sigma allowable. So for example, let's say if I'm not sure about the materials of these two, let's say, so what he says, on which condition the pinion is weaker. So pinion is weaker if, for example, you know, for pinion and gear, BM will be same, width and module will be same. And let us say if I'm not sure about the material, what kind of material is that, then obviously this value will be different, can be different from gear as well as pinion, because the material may be different. It means, and y will also be different for pinion and gear, and you know the y will be lesser for pinion. So it means the combination of this y and sigma allowable will decide which one is having, which will carry less value of this maximum tangential tooth load. So in this case, if he is saying that pinion is weaker, so if pinion is weaker, then this combination of this y and sigma allowable should be lesser for pinion. So if it is lesser, it means it will carry less load. That is the meaning of this. So out of all these, if you see, I think which one option is lesser for pinion? Yes, sigma b y pinion is lesser than sigma b y pinion. Yes. So this value, if this combination is less for pinion compared to gear, then we will say it will carry less maximum load, less maximum tangential tooth load. So it means we will say in this case pinion will be weaker, right? If this combination is weaker, less for that, right? So that is how you have to decide. The same equation that we used. So C is going to be the correct option for you. Let's now move on to the next one. Just see this one. Okay. ratio factor for internal and external gear pair. So I think here you can make a mistake, but I think you may not find the correct answer. But because there are, I think, some mistakes over here in every this, there are going to be 2. Okay, now if that be the case, where in which equation you find out the ratio factor? In gear design, particularly when we talk about the basic design of spur gear, you are having only 2 design equations. One is for wear strength, other is for the beam strength, that is a bending. So this ratio factor emerge in your wear strength equation. Wear strength is dp b k q, and over here this is the diameter of the pinion, width of the pinion as well as gear, because it is going to be same. So k is the material combination factor, whereas q over here is the ratio factor in this equation. And ratio factor, as you know, if it is a external meshing, then in that case it is going to be 2 number of teeth on gear divided by number of teeth on pinion plus number of teeth on gear, if this is a external meshing. But if it is an internal meshing means one gear will be external, the another one will be internal. So I can say this is an internal meshing. So in this case, it is going to be minus sign over here, 2 tg divided by teeth on gear minus teeth on pinion. So over here, z, it has been denoted by this. So this option B, 2 tg divided tg minus pinion, number of teeth on gear minus pinion. So you should have clarity about this. For example, what is material combination factor? He may check your understanding about that also, ratio factor also, and all that. So directly he will frame the direct questions based on those equations. So correct option is going to be B, right? So keep it in mind, this is 2. Just don't forget to put 2 value over here. So B is going to be over there, 2 tg. Let's go to the next one now. Just see this, go through the statements. To avoid the bending failure, the beam strength of the gear tooth should be what? See, beam strength is the maximum tangential tooth load it can carry without bending failure. And what is the actual tooth load? Actual tooth load, we have said that actual tooth load will we have to take the dynamic effects into account. So actual load which will be acting over there in the last one of the earlier question I told you, that is that this is a static load that will always be acting divided by kV, and this value will be greater than PT because this will be in fraction, or you will say this will be PT plus kV. So this is the net load which is acting between these 2 gear tooth in running condition, including the effects of dynamic effects also. So net load acting over here is this one. So beam strength, that means the maximum load that this gear tooth can carry without bending failure. So in any case, the capacity, this value of load which is actually acting should not be more than its bending capacity, right? So bending capacity is what? Beam strength. So in any case, this load should be less than the actual effective load acting on that. So beam strength, or the maximum load that gear can carry without bending failure, that is beam strength, should always be greater than the actual load, which is effective load acting on the gear tooth in the running condition. So see, to avoid the bending failure, the beam strength obviously should be greater than the effective load between the meshing teeth. B. Okay, so let's go to the next one. Stub tooth in gears. What is the meaning of stub tooth? Okay, so see, we have different kinds of teeth. Like we are saying that standard teeth, full depth, जिसको हम बोलते हैं, we are having a full height tooth. So sometimes we can shorten the tooth. For example, if you have a look just over here. So for example, if this is a standard tooth, so full height, you can say from top to bottom. But in case of stub tooth, if you see, what we have done is we have removed some portion from the top, right? So for example, this may be done. So that means actual height of this gear tooth, stub tooth will be smaller than that, right? That of the compared to the full depth gears. So if you just see visually also it appears. So you can just remember it from the stubble. Stubble is, sometimes you say stubbles you call for the hair also on your like beard when you cut it. And at the same time, sometimes, for example, you're having a grass which you have cut from the bottom. So there also you're having that stubble. That means small part. So you can just remember it. That is a smaller than the standard gear tooth, and it may be used in some application where there's a chances of interference and all that, to avoid that. Okay, so let's go to the next one. Interference is inherently absent in the following type of gears. Two gear tooth profiles that we know or that we use, or right now we are using, like we use involute, which are very prominent now. But there is another one called as cycloidal, right? But in cycloidal, they have one of the greatest advantage in the form of interference doesn't take place in those. Whereas in involute, even they are easy to manufacture, easy to make, because you make use of only one profile. In cycloidal, to make the gear to complete profile, you have to use the multiple profiles. And also the pressure angle is not constant over there. Whereas in case of involute profiles, you have the constant pressure angle, only one profile of the gear tooth you have to use. So easy for us to manufacture and use also and interpret also, compared to cycloidal. But they have a problem of interference in case of involute gears, which you study in this case in this chapter. But in case of cycloidal, you don't have that problem of interference, right? So that means in cycloidal gears, you don't have that problem of interference. Okay, go to the next one. Which one of the following is the lubrication regime during the normal operation of a rolling element bearing? Just need to think a little bit over here, and then I think you can get the idea. So in case of a rolling element bearing, for example, when it is in operation, sort of all these, which type of lubrication mechanism is in operation? Okay, so first thing that you can just very easily recall or just think of is that, okay, you are having inner and outer races, and these balls are basically putting pressure on that inner race or outer race depending upon its location. So there is going to be point contact and load will be exerted. So but at the same time, when they are rotating at a certain speed, these, when they exert the force, then because these members are elastic in nature, so locally they are going to compress by a small amount, and that small compression basically create a gap for that particular lubricant to come in between that, and therefore try to separate it. If you have to get the idea, then just have it's a typical case of elasto-hydrodynamic lubrication. That is, what you are having is, if you see over here, this is highly enlarged view. If you see, this is a ball, let us say, it should have been this way, right? And race should have been also perfectly, if you say, it should have been this way. But what is happening is, because of the rotation and pressure that is getting generated, the ball is slightly getting compressed, deformed, you can say elastically deformed. That is why the name is elastically getting deformed, and creating the space for that oil to get inside. And at the same time, since rotation is also taking place, that energy will try to create a pressure, a little bit pressure over there, and therefore that lubricant gets inside over here. So that is why two operations, that means elasto and hydrodynamic lubrication, you already know, that is a lubrication mechanism in which that lubrication layer is created, that lubricant layer is created because of the pressure generation, which that energy that you get from the rotation of that particular lubricant by that shaft. In case of shaft, over here similar kind of mechanism happening over here, because oil is also getting rotated during the whole rotation, and therefore it gets inside little through pressure and little through elastic deformation, right? So it is not a case of hydro, that means it is purely you can say this is one of the best case for the elasto-hydrodynamic lubrication, right? So you may think of boundary, because this example would look like your boundary lubrication. For example, in hinge, door hinge, you are having a boundary lubrication. You are having a in the machine tool slide, लेथ में जो आपका जो स्लाइड है, जो स्लाइड करती है, उसमें क्या होता है, यू आर हैविंग दैट पर्टिकुलर lubrication, but metal to metal contact is predominant over there. Lubrication है, बहुत thin layer है, but metal to metal contact is dominant, very much dominant over there. But here that much, because ये rotate जब एक certain speed पे rotate करिए तो आपका hydrodynamic lubrication, your hydrodynamic lubrication part is also coming into picture, right? So that is why we are saying this is a case of elasto-hydrodynamic lubrication. Okay, I think you must be able to answer this. The ability of bearing material to accommodate grit, small particles, you can just think of grit means small particles and dust particles, etc., without any scoring. Scoring means without producing any kind of scratch and all that of the material. The journal is called, scoring of the material of the journal is called, क्या बोलते हैं हम उसे? What is the property that where these grits and dust particles are accommodated? We call it as a embeddability, right? Yes, you're embeddability, embedded. That means the small particles gets embedded on the surface. So if they gets embedded, right? Okay, right. If they gets embedded, it means they cannot scratch the surface. For example, if you are having a hard particle and that the surface is also hard, so obviously it cannot go inside that particular surface. If it can go, then obviously the only option is scratching that particular during the rotation, when the metal small contact will take place, right? So we call it conformability is the change in the shape, adapting the shape. That if, for example, if you're having a ball, so you press it, it takes the shape, may take another shape. So conformability is that property. But embeddability, particles getting embedded in the other material, and in the process it is not able to produce the scratch and related things, right? So we call it as a embeddability. Corrosion resistance, you already know, that is without corrosion because of that. Okay, so let's go to the next one. If the size of standard specification, if the size of a standard, not specification, just mend it a little bit. Specimen, this is not specification, this is a specimen. Specimen का मतलब हुआ sample, test sample. Specimen for fatigue testing machine is increased, the endurance limit of the material will, right? So what is the option? See, what happens is when the size of the specimen you will increase, so this is the endurance limit, right? Let us say this is the maximum amplitude of completely reversing stress that material that it can carry. ये maximum amplitude है, let us say ये carry करता है, right? इसको हमने SC बोल दिया, right? This one. So बोलता है what happens if sample size is increased? Let's say this is the standard sample size, but you increase the size. So see, when the sample size increase, the possibility that somewhere within the material defect may exist. Will exist or not, that is not, we are not sure, but we go by the probability that, okay, larger the component, the probability that somewhere some kind of defect may exist. And if defects may exist somewhere, then what happens is that stress concentration will take place, because that defect acts like a discontinuity. And you know, when you are having a discontinuity, the stress concentration will take place. And if stress concentration will take place, then it means actual value of stress will be far higher. If stress is far higher, then your ability to carry out this amplitude of the stress will reduce for unlimited number of stress cycles, right? So that is why you say that if you will increase the size of that specimen or even component, simply also you say that the endurance limit of that component will component or specimen will decrease. So you're going to have the C as a correct option. Okay, I think it's more of a straightforward question rather than a complicated one. So Gerber line is a failure criteria. You know, when do we use? अगर मैं आपसे question पूछूं, when do we use these criteria, Goodman, Gerber, and all that? Do we use it in the completely reverse stresses? So of course not. You know, we use them in case of when the component is subjected to what? When the component is subjected to fluctuating stresses, where you have both mean, component, and amplitude of stress. So then these three criteria will be used. for designing a component for unlimited number of stress cycles. If you have to design the component which is subjected to completely reverse stresses, then I have SN diagram. If it is a case of completely reverse stresses, then SN diagram is sufficient. But if it is a case of fluctuating stresses, where you're, because in completely reverse stresses your mean is 0, in fluctuating stresses your mean is there as well as amplitude is there. So when a component is subjected to a combination of mean and amplitude, we use these criteria. You know, this is Soderberg, this is Goodman, and this is Gerber. Clear? So it is in the form of a parabolic curve, for which he has given the equation that you may be knowing. So this is how you have to see. You also have to know that which one is conservative and all that. That part also you can see. Okay, so D is going to be the correct answer. Just have a look over here. Remaining 2 lines, they are also used for the same purpose. Other are lines. Yes. Okay, you are saying that, okay, remaining 2 straight lines. Remaining are straight lines, right? Okay, go through this question. To avoid tearing of the plate at the edges, the safe distance from the center line of the rivet's hole to the nearest edge of the plate should be equal to. See what he's talking about. To avoid tearing of the plate, ध्यान रहे, at the edges. Tearing of the plates at the edges is different from tensile failure of the plate. Right? Tearing of the plate at the edges. So tearing is also a tensile failure, but at the edge. Whereas when we talk about the tearing of the simply plate, then it means we are talking about the tensile failure of the plate. So it means he's talking about this kind of failure. Right? This is just one rivet which has been shown to you, but you know, you could have a number of rivets over there. Like you could have, if the plate width is more, so you could have more number of rivets. So at the edge, what may happen is, if this margin, you know, from the edge to the nearest row of the rivet, you already know, we call that as a margin. Which one? Center line of the nearest row is this one. And from here, we call this distance as a margin. And or over here, if I ask you which one is the margin, let's say had it been a plate, so you will say this is the center line of this nearest row of the rivet from this edge. So I will call it as a margin. So if this margin is not sufficient, then the plate, this plate may tear out this way. फट गई, ऐसे फट गई है. तो इसको we call it as a tearing. Tensile failure बोल सकते हो, because it is tearing out this way. But they're at the edge. Now, normally we don't follow a kind of elaborate procedure for design of that particular plates over here. We simply go by taking sufficient margin. And normally it has been observed, or jo empirical results hain, if you take, let us say, margin at least equal to 1.5 times the nominal diameter of that particular rivet, nominal diameter or diameter of that rivet, then we will say that this kind of failure will not take place. So how much you should take? At least take this margin equal to 1.5 times diameter of the rivet. That's all. So our job is done. So that is why, if you know, when you may have studied the design equations that we talked about, so we say that usually, not always, but usually we say that it is taken equal to the 1.5 times diameter. So why we say that? Okay, that margin we can avoid the failure at the margin area. So this is going to be the answer. Go through this. Logic, Nalin, you can use the logic, but then you have to do the PhD. Apply the logic, go for PhD, go for masters. Point is, you can apply the logic, but point is where you see that, okay, significant advantage you are going to get. ऐसी जगह एनर्जी नहीं लगानी है जहां पर आपको जो है सिग्निफिकेंट रिजल्ट नहीं आए. इंपीरिकल बहुत सारे रिजल्ट इन प्रैक्टिकल, एज ए प्रैक्टिकल इंजीनियर you have to get the empirical के बेसिस पे उल्टी लगा चलते हो आप. ऐसे नहीं चलता कि पहले क्या थ्योरेटिकली किया फिर. यस, मोस्ट ऑफ द केसेस व्हिच आर क्रिटिकल विद देयर यू गो, बट until unless, क्योंकि हर एक के लिए आपके पास इन्वेस्टिगेटिव रिजल्ट नहीं हो सकता, थ्योरेटिकल रिजल्ट नहीं हो सकता. तो समटाइम्स वी हैव गो विद द empiricals also, right? So you can go, if you want to produce a thesis that, okay, you want to go ahead with you want to carry out the detailed analysis, why I will take 1.5, I will not take, I will produce some kind of equation. Nobody is stopping you. Okay, you can publish the paper on that. Failure of the roller bearing takes place due to bearing takes place. It is not leaks, right? Failure in the roller bearing takes place due to what? Failure in roller bearing takes place due to fracture of race, fatigue, high temperature, plastic deformation. Okay, which one out of these is basically can lead to the failure of the bearing? So you may have seen that bearings are balls of the bearings as well as the races of the bearings. They are subjected to stress reversals. Whole system is rotating. So when they are subjected to the stress reversals, it is a case of fatigue loading, and that means the stress reversals. So it means the failure of the component takes place because of the fracture. But fracture, the most dominant fracture, fatigue failure, basically it is a surface fatigue failure. Because it is not that ball will completely fail. So what happens is that the strength of the as a whole ball may be significant enough, but जो surface है उसका, ball का surface है या race का surface है, that surface of the race that may fail, right? जैसे हमने बात की, ये भी क्या था? What was that? गियर के केस में ये कौन सा फेलियर था? पिटिंग. That was nothing. पिटिंग हमने बोला था उसको, बट क्या था वो? That is also a surface fatigue failure. पिटिंग कैसे हुई आपकी? Repetitive loading. अभी जो है कांटेक्ट हुआ आपका, then load is released, then दोबारा जो है जो टूथ है, it will rotate, it will come back and then exert the force, then the load is released and then so it means repetitive cyclic loading is taking place and therefore surface में जो है वो क्या होगा? Surface fatigue. Instead of this tooth getting failed, क्योंकि टूथ की स्ट्रेंथ सिग्निफिकेंट एनफ हम ले ही लेते हैं डिजाइन के बाद, हमने ले ली कि कितना साइज होना एंड ऑल दैट, सो वी आर सेफ फ्रॉम दैट. बट दिस वी कैन नॉट अवॉइड बिकॉज सरफेस. यस, द ओनली वे वी हैव इज टू इंक्रीज द हार्डनेस ऑफ द सरफेस, दैट वी डू ऑलवेज. बट यहां पर जो सरफेस फैटिग फेलियर है, तो यही सेम सिचुएशन क्या है? बॉल्स और रेसिस, आपका जो रेसिस के ऊपर जो बॉल जो है रोटेट भी कर रहा है और घूम भी रहा है, लोड अप्लाई कर रहा है, सो इन दिस केस सरफेस के ऊपर रेसिस में भी ऑल्सो फेल और balls may also fail. So it is not the fracture of the race. Yes, it may, race may also fracture completely. The possibility exists. But the dominant failure that you will find is going to be the fatigue. And he has written the fatigue, but we more appropriately, it is the surface fatigue failure. Surface fatigue failure. किसका? It could be a ball का surface का fatigue failure भी हो सकता है. That pits may get created on the ball or pits may get created on the races also. Okay, so ये रिलेट करने हैं इसमें, ये भी सरफेस फैटिग फेलियर है, ये भी सरफेस फैटिग फेलियर है, राइट? लेट्स गो टू द नेक्स्ट वन. Okay, so what do you say? A shaft is made to rotate in anti-clockwise direction at high speed. Go ahead with this question, and all of you must be able to answer this. Any answer? Okay, you know, in case of hydrodynamic, a shaft is made to rotate in anti-clockwise direction at high speed. The position of the shaft inside the bearing, you know it very well. You know, when I will rotate it, you are having a lubricant over here, and since it is rotating in this direction, pressure will build up from this side. And when the pressure will build up from this side, then it will try to create sufficient pressure to lift it, but at the same time, it will try to shift it to the other direction. So you have to see the direction of rotation. So if it is rotating this way, then obviously pressure will be created to lift it. When pressure will be created, it will try to shift slightly towards the right. So if you see, this kind of position is going to be over there, right? So that means it will be shifted towards the right, and eccentricity will be developed over here. ये eccentricity यहाँ आएगी. See, towards the right side of the bearing with no metal to metal contact, obviously, because this is a case of hydrodynamic bearing, because you are running it at a high speed. So since you are running it as a high speed, sufficient pressure has got developed over here. And since sufficient pressure has got developed, then it is lifting the shaft, but at the same time, because it is generating that pressure from this side, so it will get shifted slightly, push the shaft to the right. It will be opposite if you will rotate clockwise. If you will rotate clockwise, then pressure will be generated on this side, and therefore it will try to shift slightly to this side. So eccentricity will be generated, so it will be shifted towards the left rather than right. So in this case, yes, clockwise. I told you, if the pressure is generated this side, if you're generating the pressure this side, if you're rotating this way, then obviously pressure will be generated this side, then obviously it will try to lift as well as push it towards the left, right? Go ahead with this. B, you're giving B. Okay. So, okay, I think I have shown it over there. Yes, I have taken this diagram, so I will make it a little big. So, when tearing, sorry, what was that? Tearing resistance per pitch length. Tearing resistance mean tensile strength, right? So, this is going to be this way. Okay. So on per pitch length basis, when we talk about, okay, in tearing, so tearing failure we consider at a cross section, right? So if we, let's say, consider this cross section, then if I ask you, because since he's asking me to calculate on per pitch length basis, tell me if I consider the width of the plate equal to pitch. So from this point to this point, let us say if I take it as a pitch, it is center to center distance, but you can take the corresponding point. They are going to be the same. If I take distance from here to here, or whether I take from this point to this point or this point to this point, it is the same thing. So if I say that what is the this width, so you have taken equal to pitch. Now if I ask you how much is the tensile stress which is developed, you will say what is the force which is acting. You said that, okay, PT, tensile force, divided by what is the force which is acting and the area which is getting subjected to tensile load, right? So area over here is on this particular width. So what is the width? If this is the, this is what? This is the diameter. So now, at this cross section, you are having diameter. So you have a hole on the plate which is equal to the diameter, right? You have a hole on the plate which is equal to the diameter, and width of the plate is this one. So effective cross section is what? Effective width is what? Width W minus D. So W minus D is the effective width, more appropriately diameter of the hole. And then what is the thickness? You are having the thickness of the plate. So force divided by area, but considering the width equal to the pitch. So it means if I talk about in terms of the tensile strength or the tearing strength of this plate, then I will say allowable value stress. When I will talk about the strength, it means this is the maximum value of the force. So if I want to get the maximum value of force, I need to input this equal to the allowable value of the stress. So allowable value of stress multiplied by this effective area, which is this one. So the same thing, if you see over here, is this. So more appropriately, it should have been what? When he's talking about the tearing resistance, then obviously tensile strength, pitch, okay, width is equal to pitch minus diameter, right? So this becomes the area. Where? This one, right? And this is the diameter, right? So this is how you will find it out. So let's go to the next one. Just go through it. So the tearing efficiency of a riveted joint. See, tearing efficiency of a riveted joint. When we talk about the tearing efficiency, it will see he's making always, in any efficiency that we talk about, he's always going to make the comparison with respect to the this strength of the unriveted solid plate. And since he has not given you any width, so again the same case that we were talking about, let us say this one is this. So let us say this is the width per pitch length basis पे आपका PA आपका width is equal to pitch and this is the diameter that you know. So what do you have? You will say strength of the unriveted solid plate. How do you write? Tearing strength. When he's talking about the tearing efficiency, that means he's talking about the tearing strength divided by the strength of the unriveted solid plate. So tearing strength of the joint is going to be what? Tearing strength of the joint, as we calculated in the last example, what was that? We said that is a stress multiplied by area. What is the area? Sorry, pitch width is equal to pitch minus diameter into thickness. So this becomes the strength of that particular joint on per pitch length basis. And what about the strength of the unriveted solid plate? Solid plate means, had I not created this hole, so what was the original width? Equal to pitch. This was the solid plate of width equal to pitch. So how much is that? This is the pitch. Is there any hole? No. So if I ask you what is the area, so in this case also you will say what is the strength of this, tensile strength of this, the same portion but without a hole, solid. So how much is that? You will say stress into what is the area? Area you will say pitch. Earlier it was here, it was pitch minus d. Here it is width is pitch into thickness is same. That's all. So this cancels out. TT cancels out. So I'm left out with P minus D divided by P. So that is I left out with 1 minus D by P. So he's asking me to calculate if I'm having that efficiency जो है वो 0.65 है, and then what is going to be 0.65 equal to 1 minus D by P ratio बोल रहा हूँ, D by P pitch. So you can say D by P is equal to 0.35, which is equal to 35%. The ratio, okay, anyway, if you don't want to say 35%, but D by P ratio becomes 0.35, right? So same way he can talk about any other efficiency also, right? So see, what we do is, you know, in case of a joint, when we say that riveted joint, then we say that strength of the joint to the strength of the unriveted solid plate, the plate without any hole. So this term is always going to be the same in any case, but this term will vary depending upon what he is asking. He may ask you that crushing efficiency. Let's say if you ask us crushing efficiency, so where in this formula you're going to have the change. This is going to be remain same, because this will remain same, but the over here, instead of tearing strength on per pitch length basis, I will write over here the crushing stress formula, right? So over here, crushing strength divided by strength of the unriveted solid plate. Same way I can do it for shear also, right? So that is how you have to remember. He can frame the question that way also. The life of a rolling bearing is classified in terms of what? Minimum life, total life, average life. So this you can answer only, otherwise if you have understanding, otherwise if you have crammed, then you will not be able to answer. You know, when we say that how we defined the life of a bearing, we have defined it as a rating life of the bearing is the number of revolutions that 90% of the bearings, then 90% of the bearings can complete or exceed. So term जो important है वो है complete और exceed, right? So इसका मतलब ये है कि मेरे पास 100 bearings हैं, and let us say 50 bearing, 20, 20, 20, 10. So 10,000, 8,000, 7,000, and then these 10 bearings I am having 5,000. So what it says that 90% of the bearings will complete or exceed. So इस set में 100 bearings में 90% bearings बताओ, ऐसी bearings, tell me those 90% bearings which will complete either that much revolution or exceed that much revolution before the generation of first crack. So वो क्या है? देखो, अगर मैं क्या करता हूं, let us say if I take 50, 20, 20, total become 90%, that is 90. So 90% of the bearings. So अगर मैं बोलता हूं कि let us say 7,000, if I take 7,000 as a life of the bearing, then it justifies this definition. Now see, these 90% of bearings will either complete 7000 रेवोल्यूशन विदाउट एनी क्रैक जनरेशन, ऑफ कोर्स ये 20 बीरिंग जो है वो 7000 रेवोल्यूशन की लाइफ दे रही है, whereas another 20 is giving 8000. So जिसकी लाइफ 8000 है वो 7000 को कंप्लीट कर ही रही है. Same way these 50% bearings are also completing 7000 revolution because their actual life is 10000 revolution. So इस केस में अगर आप देखोगे that 90% of the bearings will either complete 7000 revolution or exceed, या तो उतनी तो कम से कम करेंगे ही, बट उससे ज्यादा तो ऑब्वियसली करेंगे ही करेंगे. So it means out of all these, if you see as per this definition, it will relate to what? So ये जो पूरा ग्रुप है बीरिंग का 100 का, that will correspond to the minimum life of that bearing. So 90, क्योंकि ये रिलायबिलिटी 90% है, आप बोलोगे मिनिमम तो ये है, बट कीप इट इन माइंड लाइफ वो है, हम क्या करते हैं 90% रिलायबिलिटी. सो आई डोंट हैव टू कंसीडर दिस बिकॉज उसके बेसिस पे 10% बीरिंग्स के ऊपर हम गारंटी नहीं देते हैं. वी विल गिव नॉट 90%. सो इफ आई हैव टू टॉक बेस्ड अपॉन द 90% बीरिंग्स, तो उस 90% बीरिंग में मिनिमम लाइफ क्या है? 7000 है. तो मैं उस पूरे ग्रुप के लिए जो है बोलूंगा कि इसकी लाइफ क्या है? 7000 revolution है without any crack generation, even though I know that there are some bearings in this which have life more than that. So that is why from here life of the rolling bearing is classified in terms of minimum life के टर्म में बात करेंगे हम. So that you have to understand from this basic definition. Okay, let's go to this one. Life of a ball bearing is what? Life of a ball bearing is, okay, try to give me the answer for this question. So see, keep it in mind, यहां पर थोड़ा सा कैच है. कैच क्या है? यू नीड टू हैव डिफाइन बीरिंग की लाइफ. कैसे डिफाइन करोगे? बीरिंग की लाइफ डिफाइन करते हो नंबर ऑफ रेवोल्यूशंस पे. और ऑल्टरनेट वे क्या है? द ऑल्टरनेट वे इज number of hours, but not simply number of hours, but at some given constant speed. Because if you will not give the speed value, these two things will not match. So for them to match, ultimately होना तो उसने उतने में ही फेल है. बीरिंग ने फेल उतने में ही होना है. बीरिंग इज गोइंग टू फेल only on that much revolutions. मतलब crack is going to be generated on that much revolutions only. राइट, लेट अस से मैं बोल रहा हूं 7000 रेवोल्यूशन के बाद जो क्रैक जनरेट हुआ और लाइफ आपने दे दी लेट अस से कि 10 आवर्स 10 100 आवर्स की लाइफ दे दी. राइट, बट 100 आवर्स में वन ऑफ यू में रोटेट इट एट 500 आरपीएम, अनदर में रोटेट इट एट 1000 आरपीएम. सो उस केस में तो आपका जो वो क्रैक आपका 7000 रेवोल्यूशन में जनरेट होना है. तो until and unless these two values match, you cannot. और वो मैच कब करेंगी? when you will specify that hours multiplied by at given constant speed. स्पीड भी आपको आरपीएम में मेंशन करना पड़ेगा. सो रेवोल्यूशन तो कैसे आ जाएगा ये? देखो, आवर्स को मैंने मिनट में कर दिया, मिनट मल्टीप्लाइड बाय रेवोल्यूशंस पर मिनट आरपीएम. इसको कन्वर्ट इट इनटू मिनट्स एंड रेवोल्यूशन पर मिनट. So it will cancel out number of revolutions. So those revolutions that you will get from here must match with this. Right? So it means over here if you will see the अगर ये term, if you are not mentioning this term, then this statement is not correct. Simply just mentioning us is wrong. So इसीलिए अगर आप देखोगे इसमें जो आपका आंसर आएगा that is going to be the total only one. Life of the ball bearings is क्या है? Total number of revolutions made, ये, या number of hours at some given constant speed, at some given constant speed, until and unless he will mention this. ये स्टेटमेंट कंप्लीट नहीं है, ये रॉन्ग है, ये मैच ही नहीं करेगा आपका आप. राइट, सो until and unless you mention that at what speed you are rotating during that hours, it will not be correct. So I hope you got my point. So ये ध्यान रखना है इसका. ये आंसर इज गोइंग टू बी बी, नॉट डी. ऑन द फेस ऑफ इट इट लुक्स लाइक बोथ आर करेक्ट, क्योंकि आप वो जो क्रिटिकल इंफॉर्मेशन है वो मिस कर रहे हो. गो टू दिस वन. ठीक है, मैच कर रहा है? गॉट इट दनीश? गॉट इट नाउ? भाई अगर मैं रेवोल्यूशन में लाइफ दूं, आपको लाइफ कितनी चाहिए? दिस मच। सो दैट मींस 600,000, 6 लाख रेवोल्यूशन की लाइफ है। यू हैव ए 6 लाख रेवोल्यूशन लाइफ। 6 लाख साइकिल्स के बाद जो है वो क्या आ जाएगा? क्रैक आ जाएगा। दैट इज द मीनिंग ऑफ दिस। तो ये है। अब मैंने आपको इंफॉर्मेशन दे दी कि 1000 आवर्स। Until unless I will give you that, at what speed should I rotate in those 100 hours? कितने रेवोल्यूशन आए? 600,000 रेवोल्यूशन। तो अगर मैं क्या कर रहा हूं, 100 आरपीएम पे रोटेट करूंगा तो ऑब्वियसली क्या होगा? 600,000 रेवोल्यूशन कंप्लीट हो रहे हैं। बट अगर मैंने किया, लेट अस से इंस्टेड ऑफ दिस, आपने किया, बोला कि मैंने क्या करना, 200 आरपीएम, राइट? पे रोटेट किया आपने, गए और आपने 200 आरपीएम पे रोटेट करना शुरू किया। एंड सो सी, एज पर यू 100 आवर की लाइफ है, आपके हिसाब से तो 100 आवर्स ही है। आपने 200 में घुमाया उसको, तो ये आपका डबल हो जाएगा, राइट? 2 है तो ये आ जाएगा 12 लाख, 12 लैक्स रेवोल्यूशंस। तो आपके हिसाब से, क्योंकि अगर आप मेरे से बीरिंग खरीदते हो, इफ यू विल परचेज बीरिंग फ्रॉम मी वेयर आई हैव गिवन यू लाइफ 100 आवर्स, और आपने रोटेट किया उसको 200 आरपीएम पे रोटेट किया, तो एज पर यू आफ्टर 12 लाख रेवोल्यूशन द क्रैक विल जनरेट, एज पर यू। बट एज पर मी, मेरे हिसाब से तो 6 लाख में ही होना है, क्योंकि होना तो उसने 6 लाख में ही है। बट हुआ क्या? इफ आई एम नॉट गिविंग यू दिस इंफॉर्मेशन, अगर मैं आपको वो इंफॉर्मेशन नहीं दे रहा हूं, यू आर नॉट गिविंग यू दैट इंफॉर्मेशन कि भाई ऐसे करना, 100 घंटे तो लाइफ है इसकी, पर घर जाके 100 आरपीएम के हिसाब से बात कर रहा हूं मैं। सो दिस मच और एट दिस आरपीएम। पर अगर ये मैंने नहीं दी तो फिर तो आप बोलोगे 12 लाख रेवोल्यूशन की लाइफ होनी चाहिए थी। सो दैट इज द मीनिंग ऑफ दिस। सो इट बिकम्स क्रिटिकल फॉर मी टू मेंशन द स्पीड ऑल्सो। सिंपली आवर्स नहीं, लाइफ इतने आवर्स की लाइफ है भाई, इतने आवर्स की लाइफ है, तो फेल तो उसने इतने में रेवोल्यूशन में होना है। बट इतने आवर्स की लाइफ पे अगर 200 आरपीएम पे घुमाता हूं तो 12 लाख के रेवोल्यूशन पे ऊपर क्रैक आना चाहिए, क्योंकि क्रैक तो एक्चुअल आना आपका 6 लाख में ही है। समझिए बात? सो दैट इज व्हाई आइदर आई शुड राइट दिस वे, नंबर रेवोल्यूशन, और शुड आई राइट टाइम एट ए गिवन कांस्टेंट स्पीड। जब तक वो नहीं लिखोगे तब तक नहीं चलेगा। ओके, ओके, लेट्स गो टू दिस वन नाउ। ओके, ये जो क्वेश्चन था जो मैंने बात की, टू कैरी ए लार्ज एक्सियल लोड इन ए फ्लैट कॉलर बीरिंग, ए नंबर ऑफ कॉलर्स आर प्रोवाइडेड, राइट? सो सी, यू नो, कॉलर्स, फ्लैट कॉलर बीरिंग, ये है केस आपका, इवन दो यू कैन सी द आंसर आल्सो, दिस इज द फ्लैट कॉलर बीरिंग, राइट? सो इफ यू हैव टू कैरी ए लार्ज लोड, तो आप क्या कर सकते हो, इसमें नंबर ऑफ कॉलर्स बढ़ा सकते हो, बिकॉज द लोड विच इज एक्टिंग विल बी सपोर्टेड ओवर हियर, इट विल रोटेट दिस वे, राइट? सो मल्टीपल कॉलर्स यू कैन प्रोवाइड ओवर हियर, सो दैट वे क्या होगा, आपका जो लोड है वो, ये लोड है, डिस्ट्रीब्यूट हो जाएगा यहां पर, यहां से भी ट्रांसमिट हो रहा है, यहां से इट इज गेटिंग ट्रांसमिटेड फ्रॉम हियर एज वेल, राइट? सो दैट वे इफ यू आर अप्लाइंग द सेम लोड, देन द इंटेंसिटी ऑफ प्रेशर जो होगी वो क्या हो जाएगी, कम हो जाएगी। दैट इज द मीनिंग ऑफ इट। सो टू कैरी ए लार्ज एक्सियल लोड इन ए फ्लैट कॉलर bearing, the collar is provided, sorry, number of collars are provided, right? number of collars क्यों प्रोवाइड करते हैं हम, जब मैंने हैवी लोड कैरी करना, सो दैट वो लोड डिस्ट्रीब्यूट हो जाए, कुछ ये कॉलर कैरी करे, कुछ सम इज कैरीड बाय दिस कॉलर, सम इज कैरीड बाय दिस कॉलर, सम इज कैरीड बाय दिस कॉलर। सो ऑब्वियसली जब amount of load being carried by each collar get reduced, so intensity of pressure will also get reduced over there. So that is why decrease the intensity of pressure. Indirectly बोल सकते हो कि this load is getting distributed among the different collars. ये स्ट्रक्चर है, स्ट्रक्चर के ऊपर जो डिफरेंट कॉलर्स के थ्रू it will get transmitted. Go to this one. If K for ball bearing is this, which one of the following is correctly states the load P life relationship for rolling contact bearing? See, ये जो रिलेशनशिप है ना आपका, के तो जनरल हो गया, बॉल के लिए भी हो सकता है, उसके लिए भी हो सकता है, राइट. So ball bearing and this for roller bearing, which one of the following is correctly states the load life relationship, for a rolling contact bearings. Now when we are having a identical bearings, a group of identical bearings, तो अगर लाइफ रिलेशनशिप, दिस इज द लोड लाइफ रिलेशनशिप, लाइफ इज इक्वल टू डायनेमिक लोड कैरिंग कैपेसिटी, और ये आपका आया था लेट अस से million revolution, let us say. So let us say you are having a two identical group of bearings, right? Two identical group of bearings. So in that case, let us say for one group this is this, but keep it in mind, when we are having an identical group of bearings, the dynamic load carrying capacity for those groups is same. So इसका मतलब है चाहे ये bearing है चाहे ये bearing है, उसकी जो dynamic load carrying capacity क्या है, is same. So that is why I am not writing it C1, because if I write it for L2, दूसरी bearing के लिए बात करता हूं, तो again this is going to be this one. So now simply you can write it L2 by L1 or L1 by L2, whatever you want to write. So if I will write it, this one comes P1 by P2. This for K. So out of all these, if you see, K is a general, depending upon type of bearing, but the relationship that will hold good will be this one. Right? Over here, this is L1 by L1, this is L1 P1, it should be, if it is L2, then it should be P1 inversely. So this is the correct relationship. Got? Okay. Let's go to the next one now. Go through this one. Hydrostatic bearings are suitable for heavy loads and low speed applications. गलत है, ठीक है statement ये. What is this statement? Is this statement correct or wrong? Hydrostatic bearings purpose is to that when to carry at low speed, hydrodynamic bearing जो है low speed पे, hydrodynamic bearings at low speed cannot produce significant pressure to support the load. So that is why there we find the use of this hydrostatic bearing. Heavy load, speed is low. Am I clear? And so this statement is correct in any way. Sufficient hydrodynamic pressure is not generated in the fluid film. There is no meaning. What is he talking about? Is he talking about hydrostatic bearing or hydrodynamic bearing? So if he's talking about the hydrostatic bearing, basically he's giving the reason for this, but this is not the reason. Sufficient hydrostatic pressure is developed, only then it can support the load. Pump के through आप क्या कर रहे हो? You're supporting, providing the significant pressure so as to support the load. So ये statement गलत है. Only one statement is correct. So option C is going to be correct. See this one. Petrov's equation is used when. अब ये जो कहानी है Petrov's की, that you need to know that कहां पर, where do you use the Petrov's equation? So now just keep it in mind, Petrov's was the person who estimated the coefficient of friction within the journal bearings. उसने coefficient of friction estimate करने की कोशिश की in the hydrodynamic journal bearings. So and the coefficient of friction value that he got was 2 pi square Zn by P into R by C. And these are the dimensionless parameters. This is a bearing characteristic, and this is the clearance ratio. Dimensionless numbers हैं ये, parameters हैं. So this is the clearance ratio. Now, so this was it that he gave us. But while deriving this estimation for this particular coefficient of friction within the bearing, journal bearing, he assumed that even though actual bearing में अगर हम we will apply a load on a shaft, let's say shaft है, इसके through मैं load apply कर रहा हूं, so obviously when you will apply the load, what will happen? This will get shifted in any case, whether it is a case of hydrodynamic bearing or others also, right? So over there, when you apply the load, then obviously it will be shifted. But what he assumed when he derived this equation, he assumed that मैं इतना कम load apply कर रहा हूं, applying so small a load so that eccentricity is not developed. ये assumption थी उसकी. Based upon that assumption, he derived this equation. तो assumption ये है कि even though मैं apply कर रहा हूं load, even though I am applying the load, but at the same time, this is not getting shifted. There is no eccentricity. That means it remains concentric. ये और bearing दोनों जो है concentric रह रहे हैं. That was the basic assumption that he made. So assumption he has to make, अगर उसने simplify करना है तो उसको करनी पड़ेगी, right? So that was the, so is concentric with the bearing, coincides with the bearing, carries no, coincides जो है वो बहुत ही वेग सा टर्म है, मिस इंटरप्रेट कर सकते हो, बट अगर यहां पर इफ वी सी दिस इज बेसिकली जो है वो कॉन्सेंट्रिक विद द बीरिंग. सो वन इज ही मे आस्क यू एनी क्वेश्चन बेस्ड अपॉन द दिस की कोफिशिएंट ऑफ फ्रिक्शन एज पर द पेट्रॉफ डिपेंड्स अपॉन व्हाट दिस टाइप, कौन कौन से पैरामीटर के इनवर्सली प्रोपोर्शनल है या डायरेक्टली प्रोपोर्शनल है. सो यू नीड टू रिमेंबर दिस इक्वेशन जेड एन बाई पी. जेड यू नो इज viscosity, right? Okay, then riveted joint has lowest efficiency in case of, see जैसे जैसे आप क्या करोगे, move from lap joint towards the butt joint, and that too you are having a lap joint, then you move on to the single strap butt joint, then you go to the डबल स्ट्रैप बट ज्वाइंट. तो ये एफिशिएंसी क्या हो रही है उनकी, इंक्रीज होती है. अब ये जनरल आपको जो है दैट जनरल इंफॉर्मेशन दैट यू हैव टू कीप, मतलब ये इंफॉर्मेशन याद रखनी पड़ेगी. इट इज नॉट दैट वी नीड हैव टू प्रूव इट और समथिंग. सो एक आइडिया लेना है तो आई कैन, यू कैन थिंक, यू कैन गेट इट फ्रॉम ओवर हियर. अगेन डोंट गो इन वेरी डिटेल, जस्ट टू गिव यू एन आइडिया, राइट? देखो लैप जॉइंट्स हैं आपके रफली, इफ यू सिंगल स्ट्रैप बट जॉइंट लैप जॉइंट देखोगे 45% एफिशिएंसी. इफ यू गो फॉर द डबल स्ट्रैप बट जॉइंट एंड इन विच अगर नंबर ऑफ रोज 6 कर दे तो 92% तक बीरिंग एफिशिएंसी जा रही है. Whereas in lap joint, even if let's say a comparative comparison, let me do. In lap joint, if I'm using the number of rows of rivet 4, the maximum efficiency, joint efficiency that I can obtain is 75%. But in butt joint, that is a double strap butt joint, if I am using the same number of rows, I can obtain the 90% efficiency. Right? मतलब क्या है efficiency का मतलब है कि load that I can carry compared to the that strength of that plate is more. That is the meaning of this. तो जनरल ध्यान रखो. तो एक बोल सकते हो लैप से बट की तरफ जाओगे तो आपकी स्ट्रेंथ बढ़ेगी. सो दैट इज अ, सो इनके रिवेटेड जॉइंट हैज द लोएस्ट एफिशिएंसी इन केस ऑफ, किसके केस में होगी? सिंगल रिवेटेड लैप जॉइंट. The brakes in which friction force affects assist the actuating force. Actuating force मतलब जो फोर्स मैं अप्लाई कर रहा हूं, तो उस ब्रेक को क्या बोलते हैं? What do we call it? ये ब्रेक है, लेट से मैं क्या कर रहा हूं, उसको क्लॉकवाइज रोटेट कर रहा हूं. व्हेन आई एम रोटेटिंग द क्लॉकवाइज द ड्रम क्लॉकवाइज, तो ड्रम क्या करेगा? फ्रिक्शन, ड्रम विल अप्लाई द फ्रिक्शन फोर्स ऑन दिस पर्टिकुलर शू in its own direction, whereas the friction resistance will be offered by this shoe to this drum in opposite direction. So if I have to show the frictional forces for this situation, जब ये रोटेट कर रहा है, लेट से दिस वे क्लॉकवाइज रोटेट कर रहा है, तो इसको फ्रिक्शन फोर्स जो है म्यू आर एन बोल सकते हैं, इस डायरेक्शन में एक्ट करेगी. whereas आर एन जो है ये होगा नॉर्मल रिएक्शन, whereas आर एन इज ओवर हियर एंड फ्रिक्शन फोर्स ऑन दिस विल बी म्यू आर एन, इस डायरेक्शन में होगी. क्लियर? सो इफ दैट बी द केस, नाउ ब्रेक्स इन विच फ्रिक्शनल फोर्स अफेक्ट्स, मतलब फ्रिक्शन फोर्स कौन सी है? म्यू एन का जो अफेक्ट है, अगर ये हेल्प कर रहा है असिस्ट द एक्चुएटिंग फोर्स, मतलब ये हेल्प कर रहा है इस एक्चुएटिंग फोर्स को. व्हेन इट इज गोइंग टू हेल्प द एक्चुएटिंग फोर्स, व्हेन द मूवमेंट ड्यू टू म्यू आर एन इज इन द सेम डायरेक्शन इन विच द मूवमेंट बाय द एक्चुएटिंग फोर्स इज प्रोड्यूस्ड. नाउ सी द movement due to the actuating force is clockwise about the hinge, clockwise. What about the mu rn? Let's say ये distance है, whatever this is the distance. So mu rn is acting this way. If we see the movement, क्योंकि hinge नीचे है आपकी, if you see the movement, that is also giving the movement in the same direction. तो जितनी ज्यादा ये movement होगी, larger this movement, lesser the movement that you need to apply to exert the force. समझे? तो उससे क्या होगा कि the actuating force that I need to apply the brake will get reduced if frictional force is producing a movement in such a way that it is in the same direction in which this P is giving. So this is also giving clockwise, this is also giving the clockwise. Such situation we call as a सेल्फ एनर्जाइजिंग ब्रेक, राइट। सो द सिचुएशन, ऐसी सिचुएशन जहां भी ऐसी सिचुएशन बनेगी, अगर मैं क्या करूं, डायरेक्शन और रोटेशन चेंज कर दूं लेट अस से, तो वो सेल्फ एनर्जाइजिंग नहीं होगी। कहां गया ये सेल्फ, ये दिस सिचुएशन इज सेल्फ एनर्जाइजिंग। लेट अस से इफ आई चेंज द डायरेक्शन ऑफ रोटेशन, इफ आई चेंज द डायरेक्शन ऑफ रोटेशन, तो फ्रिक्शन फोर्स की डायरेक्शन चेंज हो जाएगी इसमें, और इसमें भी फ्रिक्शन फोर्स की डायरेक्शन चेंज हो जाएगी, म्यू आर एन। नाउ in this case this force is not helping. See the movement, this movement is anti-clockwise, this is anti-clockwise, तो अगर ये anti-clockwise है तो it will try to lift this way, मतलब ये मूवमेंट ऐसे लग रही है, so it will try to lift upward. फ्रिक्शन फोर्स के कारण मूवमेंट, द मूवमेंट ड्यू टू द फ्रिक्शन फोर्स is acting clockwise on this lever assembly. If it is acting anti-clockwise, then it will try to lift that lever. If it will try to lift it, so you need to apply more force or the more movement in this direction. So it is not helping this movement. So these two movements are in opposite direction, this and this. So we say this is not a self-energizing case. Self-energizing का मतलब है कि वो help करे in reducing the actuating force, but ये help नहीं कर रही है इस situation में, right? That is how you have to see. Is going to be answer. Let's go to the next one. In case of eccentric riveted connection, the rivets have to resist. Just go through this. सी ऐसा है कि इस क्वेश्चन में अगर तो वो कॉपी पेस्ट करेगा, अगर तो उसने कहीं बुक से, दैट मींस दोस बुक्स वहां से कॉपी पेस्ट किया क्वेश्चन, तो यू आर लेफ्ट आउट विद नो चॉइस। रीजन बीइंग उसने क्लैरिटी नहीं दी, ही हैज नॉट गिवन यू क्लैरिटी व्हाट काइंड ऑफ दिस जॉइंट इज, बट हम ये अज्यूम कर रहे हैं दैट ही इज समथिंग सेइंग दिस वे, दिस इज द एक्सेंट्रिकली लोडेड रिवेटेड जॉइंट। बैक प्लेट है, एक फ्रंट प्लेट है, बैक प्लेट फ्रंट प्लेट ज्वाइंट विद द रिवेटेड ज्वाइंट, यहां पर 4 रिवेट्स लगा दी उसको ज्वाइन करने के लिए। सो व्हेन यू विल अप्लाई दैट लोड, देन ऑब्वियसली यू विल से दिस विल एक्ट दिस वे, इट विल ट्राई टू रोटेट इट। ट्राई टू रोटेट मीन यहां पर इंटरफेस के ऊपर जो रिवेट्स का जो ये क्रॉस सेक्शनल एरिया है, इसको क्या कर रहा है, वो रोटेट करने की कोशिश कर रहा है, ट्राइंग टू रोटेट इट। तो वन इज द टॉर्शनल शियर स्ट्रेस ऑन ऑल द रिवेट्स, और जो बाकी बचा वो क्या है, इसका इफेक्ट यू नो व्हेन वी विल ट्रांसफर इट टू द सेंटर, दिस इज एक्टिंग ओवर हियर, देन इट विल ट्राई टू, if I want to replace it completely, this is what I can say. I can replace it this way. One is movement and the other one is P, the force coming over here. So if that is the case, I can remove now. So I have to consider the effect of this. So movement का effect तो मैंने देख लिया, it will try to rotate. Whereas what about this vertical force which is trying to push it downward? Again, it is also trying to shear it. It is also trying to shear it. So direct shear and torsional shear. So it means direct shear stress and twisting stress. So I hope ये थोड़ा ध्यान देना, you could have other cases also जहां पर riveted joint अगर थोड़ा कॉन्फ़िगरेशन अलग होगी, तो वहां पर कोई जरूरी नहीं है कि सर व्हाट इज द डिफरेंस बिटवीन द डायरेक्ट शियर स्ट्रेस एंड ट्रांसवर्स शियर स्ट्रेस, मीनिंग इज सेम। इस केस में बोल सकते हो ट्रांसवर्स ए आपने डायरेक्ट शियर स्ट्रेस और ट्रांसवर्स यू आर ट्राइंग टू कोरिलेट इट थोड़ा डिफरेंटली, बिकॉज ट्रांसवर्स कहीं और बात कर रहे हैं, ट्रांसवर्स ऑफ परपेंडिकुलर टू द एक्सिस या लॉन्जिट्यूडनल एक्सिस। सो हियर आई थिंक वी विल नॉट यूज द टर्म ट्रांसवर्स शियर स्ट्रेस। डायरेक्ट का मतलब हुआ कि सिंपली व्हेन आई एम अप्लाइंग द डायरेक्ट फोर्स, दैट फोर्स इज डायरेक्टली ट्राइंग टू शियर दैट पर्टिकुलर कंपोनेंट, उसको डायरेक्ट शियर बोलते हैं। क्लियर? ट्रांसवर्स शियर जो है वो कंसेप्ट आपका वहां आ जाता है, कहां पर, इन केस ऑफ दिस वेल्डेड जॉइंट्स, डिपेंडिंग अपॉन द डायरेक्शन ऑफ लोड। बट ये दोनों इस केस में आई थिंक डजंट मेक सेंस। फॉर एग्जांपल अगर मैं बोलूं ऐसे कर रहा हूं तो भी डायरेक्ट शियर है, डायरेक्टली इट इज शियरिंग दीज पर्टिकुलर रिवेट्स। अगर मैं बोलता हूं नहीं इस प्लेट को मैं ऐसे नहीं कर रहा हूं, ऐसे खींच रहा हूं, तो भी क्या है, देन ऑल्सो यू आर शियरिंग ऑल दीज रिवेट्स ऐसे, बट डायरेक्टली शियरिंग, कि वो फोर्स डायरेक्टली जो है उसके ऊपर आ जाए। जैसे फॉर एग्जांपल इफ वी से टॉर्शनल शियर स्ट्रेस, सो दिस इज नॉट डायरेक्ट, अप्लाई कर रहे हो आप मूवमेंट, और उस मूवमेंट के कारण फोर्स लगी और उसने शेयर किया। अगर मैं इसकी बात करूं तो आपने किया मूवमेंट अप्लाई की, इस मूवमेंट ने यहां पर कोई फोर्स अप्लाई की ऐसे। नाउ ये जो फोर्स है इसको कैसे शेयर कर रही है, ऐसे जब रोटेट हुआ ये, तो ये क्या कर रही है, ऐसे शेयर करने की कोशिश कर रही है। समझो बात? सो that is, I hope you may have got the little idea. वेल्डिंग का कहीं क्वेश्चन होगा तो डिस्कस कर लेंगे उसको, ट्रांसफर जो बोल रहे हो, बट आई थिंक यहां पर बहुत ज्यादा सेंस नहीं मेक कर रहा है। ओके, डिजाइनिंग ऑफ फॉर बोल्ट इज डन ऑन द बेसिस ऑफ, ये क्वेश्चन भी थोड़ा सा अगेन उसी लाइन पे है जैसा लास्ट क्वेश्चन था, बहुत ज्यादा क्लैरिटी नहीं है, बट आपके पास कोई और ऑप्शन है भी नहीं, यू डोंट हैव एनी अदर ऑप्शन। रीजन बीइंग, इन दिस केस अगर व्हाट इज एज्यूमिंग क्योंकि उसने जो है ही हैज नॉट गिवन क्लैरिटी ऑन द स्टेटमेंट, ही इज एज्यूमिंग दिस इज हाउ द सिचुएशन इज। Okay, these are two plates joined by nut and bolt. So what he's saying, designing the bolt is done on the basis of what? Now, इस case में what he is assuming, even though he has not mentioned, but based upon his जो उसने option दिए हैं, all those options that he has given is this one, कि लोड वो ऐसे अप्लाई कर रहा है, कहां से आया? He has framed the question, but this is how it is. So you are left out with no option. तो अगर इस ये केस है आपका, तो in this case obviously what is happening, you are pulling it, you are pulling that particular bolt, इसके थ्रू बोल्ट के ऊपर गई और बोल्ट को पुल कर रहे हो, सॉरी मतलब ऑब्वियसली नट के थ्रू बोल्ट एंड बोल्ट इज गेटिंग पुल्ड, तो टेंसाइल, सो वन इज टेंसाइल लोडिंग, ओके दैट इज ओके। सो नाउ टेंसाइल में देख लो कौन कौन से हैं आपके, ये तो गया आपका कंप्रेसिव अलोंग विद हाई, ये भी गया, ये भी गया, यू लेफ्ट आउट विद ओनली दिस ऑप्शन, राइट? सो यू लेफ्ट आउट विद ओनली बी ऑप्शन। अब दूसरी ऑप्शन जो अगर मैं कहूं कि हैड ही, लेट्स से एम्बिग्यूटी है, बट इफ द लोडिंग इज नॉट दिस, ये लोड ऐसे नहीं है, भूल जाओ अभी इसको, राइट? फॉरगेट अबाउट इट। लेट्स से लोड ऐसे है, केवल ऐसे है, लेट्स से यू आर अप्लाइंग द लोड on this bolted assembly on this way. If I ask you what kind of stress is getting developed on the bolt, it's pure shear only, rivet ही नहीं होगी ये, it's something like rivet only, तो you are simply shearing, direct shear, इसको बोल सकता हूं डायरेक्ट shear, क्यों? ये फोर्स डायरेक्टली इसको शेयर कर रही है, यहां पर ये पोर्शन इस तरफ आ रहा है, वो पोर्शन वहां जा रहा है, ये शेयर हो रहा है यहां पर, तो वो ऑप्शन तो कहीं है ही नहीं। डायरेक्ट शेयर स्ट्रेस, केवल शेयर स्ट्रेस, इन दिस केस ओनली डायरेक्ट शेयर स्ट्रेस शुड बी ओवर देयर, बट दैट ऑप्शन ओनली सिंगल डायरेक्ट शेयर इज नॉट ओवर देयर। बाकी होगी भी कॉम्प्रेसिव, आप बोलोगे कॉम्प्रेसिव भी हो सकती है सर, क्योंकि आप खींच रहे हो तो यहां पर कॉम्प्रेशन हो सकती है, बट दैट इज इनसिग्निफिकेंट डिपेंडिंग अपॉन, क्योंकि सिग्निफिकेंट लेंथ होगी। सो फॉर मी एरिया ऑफ कंसर्न इज दिस वन, सो इसलिए ये तो हम भूल ही जाएं। सो वी आर लेफ्ट आउट विद कि इसने अज्यूम किया ये कॉन्फ़िगरेशन, तो इसमें टेंसाइल, हाँ इसमें भी शेयर होती है यहां पर, बट दैट शेयर वी डोंट कंसीडर बिकॉज वी हैव टेकन द हाइट ऑफ द नट, सिग्निफिकेंट हाइट ऑफ द नट, बिकॉज यहां पर जो शेयर है थ्रेड्स में इस तरह की शेयर होती है, आई थिंक वी हैव डिस्कस्ड इन द क्लास ऑलरेडी। सो जो सॉरी जो शेयर होती है, दैट इज द थ्रेड्स व्हिच मे गेट शेयर्ड, दैट इज अ डिफरेंट काइंड ऑफ शेयर, बट क्योंकि हमने वी हैव टेकन द सिग्निफिकेंट हाइट ऑफ, स्टैंडर्ड हाइट ऑफ नट जो ज्यादा लेते हैं, तो दैट कैन बी इग्नोर्ड, सो इसलिए द मोस्ट एप्रोप्रिएट आंसर इज गोइंग टू बी B1. Just go through this. Okay, shearing efficiency of the, I think I explained you, right? Like we said that tearing efficiency, हमने क्वेश्चन किया तो हमने कहा tearing strength of the joint divided by unrepeated solid plate. Same way, if he asks you instead of tearing, if he asks you shearing efficiency, तो नीचे वाला पोर्शन तो सेम रहेगा, अनरिवेटेड सॉलिड प्लेट, वो तो टेंशन में ही रहेगी, राइट? अनरिवेटेड सॉलिड प्लेट, नो होल, अनरिवेटेड में नो होल ऑन द प्लेट, सॉलिड प्लेट, स्ट्रेंथ ऑफ द अनरिवेटेड सॉलिड प्लेट, एंड यहां पर क्या होगा, दैट इज द shear strength on per pitch length basis, shear strength on per pitch length basis, that's all. So that becomes shearing efficiency. So if you see over here, shear strength per pitch length, strength of the riveted joint. No, not of riveted joint. ध्यान रहे, strength of the riveted joint, you know, is a lesser of all those strength, tensile, compressive, and shear. Out of all those, which one is lesser? That is the strength of the riveted joint, right? Whereas it is a shearing strength per pitch length and the strength of the unriveted solid plate. अगर वो ऐड करना चाहता on per pitch length basis, comparison you have to do. Here if you are doing it per pitch length basis, over here also you have to do solids on per pitch length basis. So this is the correct answer. Right, it's the same thing. Go ahead with this. Splined shaft. I think this is a relatively easier. The splined shafts are used for so basically spline. I hope you understand the meaning of splines. आप क्या करते हो? You provide the recesses. जैसे shaft है, इसके recesses यहाँ provide करते हो आप, so that let's say if you install something over here, gear or something, so it can be moved along the length of that particular shaft. जैसे for example gear shifting करते हो in your car or in your bike, when you change the gear, so basically you're moving that gear on that particular spline. यहाँ पर gear attach किया होगा, उसको आप उसके ऊपर move कर सकते हो. So that is the purpose of providing the splines on the shaft. Axial movement between the shaft and the hub. Similar question we did, पर यहां पर थोड़ी सी चेंज होगी. Similar question we did, but the only thing that we have over here, उसने speed को change कर दिया. What he did, instead of the high speed, what he has mentioned is the slow speed. So if you are rotating, ध्यान रहे, if you are rotating a shaft, initially यहाँ इस position पे था ये, let us say, and sorry, एक और figure बनाना पड़ेगा मुझे. So when it anti-clockwise starts rotating, see, initially, even though you have lubricant, but at the bottom you don't have any lubrication. Right? Lubricant is over there. So what happens is, so because of the friction over here, this surface will offer a frictional resistance. So होता क्या है, शुरू में ये उल्टी डायरेक्शन में मूव करता है इसके. So it moves slightly in this direction. So it means climb on this. So actual position at very low speed is something this way. That means it climbs on the something this way. So it will move towards the. अभी pressure develop नहीं हुआ. Keep it in mind. Speed is very low. So pressure has not generated. So since the friction resistance is more, so it is trying to rotate. So that due to rotation, because of friction resistance, it will try to give the resistance in this direction, and therefore it is lifted a little bit on this side. But as you go on increasing the speed, then sufficient pressure will be developed over here. Then it will be pushed toward the right. So actual position, the final position, that question that we did was this way. So it was rotating this way, and then it shifted from the center towards the right because sufficient pressure has got developed. There is no metal to metal contact in this case at high speed in running condition. But over here, as it has just started rotating, friction is over there, metal to metal contact remains, and it will move towards the left. So has a metal to metal contact and is placed left. ये situation. So ये आपका correct answer आएगा. If let us say situation reverses, if this rotates clockwise, then same way it will shift towards the right. जैसे ये left की तरफ shift हुआ, it will shift towards the right slightly because of friction at low speed, and metal to metal contact will be there. And when full running condition, then it will shift towards the completely toward the left in such position towards the left with no metal to metal contact. Okay, so just keep note of these fine things. Go ahead with this. Factor of safety for fatigue loading is expressed as factor of safety, like you're having on the similar lines that you know, like in endurance, sorry, when you have a fatigue case, or let us say if you talk about completely reversing, then this becomes the endurance limit becomes the criteria, right? So this is the maximum value of stress that you can apply. It is on the similar line you are having, let us say, when you know the yield is this one, yield strength is this one, but actual value of the stress that you will apply over here will be lesser than that. We call that as a stress as allowable, right? If I ask you what is this, you will say this is a margin of safety or factor of safety. Over here you will say factor of safety is, that is by what margin this actual value that you are applying is lesser than the yield strength. So you'll say yield divided by allowable. Obviously जितना आप allow कर रहे हो वो उससे कम ही होगी. Same is going to be situation over here. Like over here in completely reverse stresses, endurance limit is the criteria. ये तो limit होगी, like यहाँ पर yield थी. So actual value of the maximum stress that you will apply over here, let's say allowable amplitude of allowable stress, actual amplitude of allowable stress, that has to be less than this amplitude, that is the endurance limit. तो उससे नीचे ही होना चाहिए कितना, by factor of safety. So if I ask you how should I write factor of safety over here, on the same way, like limit was SC over here, endurance limit, and allowable is this one, और allowable इसको थोड़ा सा amplitude allowable ऐसे बोलो, maximum stress भी बोलो तब भी चल जाएगा, because in this case it is a completely reversing stress. So anyway, so parallel comparison can be drawn. So over here endurance limit वैसे भी, so he may confuse you with the endurance limit with other parameters, but यहाँ पर क्योंकि straightforward दिया तो it is easy for us, क्योंकि endurance limit he has not mentioned endurance limit in any other case. So इस case में fatigue में तो definitely endurance concept आएगा ही आएगा. So even if you don't know, you don't have very clear understanding or difference, तब भी you will be able to answer, because you will say that fatigue endurance is related to fatigue, and this will be my answer. Okay, so go through this one. Stress concentration takes place Q2. Okay, so I think almost many of you have answered. Okay, so stress concentration, when we say stress concentration is because of discontinuity, as simple as that, right? So now when we talk about the discontinuity, so that discontinuity could be in any form. Discontinuity is a general name, so it could be in any form. So variation in material property. So if material properties vary from point to point, let us say, so it means indirectly इसका मतलब ये है कि somewhere that material is not uniformly distributed. So that may be kind of interpreted as a kind of a point for material is not uniformly distributed. It means discontinuity may exist because in the redistribution of the material, and therefore stress concentration may take place. Abrupt changes in the section is pretty clear. Changes cross section में बहुत ज़्यादा है section में. And pitting of the at the various point, again pitting हमने discuss किया है, kind of pits or the discontinuities. So all of them are going to the stress concentration factor. Okay, go to this one. So what it says that stress concentration factor is the ratio of what? So you know it already. Stress concentration factor is nothing but, let's say theoretically बात कर लेते हैं. So it is the ratio of actual value of maximum stress to the maximum value of the stress as per formula, right, at minimum cross section. That is the, okay, I hope you understand. So यहाँ discontinuity में the actual value of stress will be far higher than calculated by the formula. As per your formula, इस discontinuity में you have maximum value of stress जिसको नाम दिया nominal. कौन सी? ये nominal value of stress we also call, but this is the maximum as per formula, P divided by minimum cross section area. So nominal is nothing but maximum value of the stress as per the formula, this one. This is or nominal. Whereas actual value of stress over here is far higher than this that you have calculated from the formula, that is this. So जब हम ये फॉर्मूला लिखते हैं तो हम ऐसे लिखते हैं KT is equal to maximum value of the stress divided by nominal value of stress. So maximum कौन सी? Actual. ये कौन सी है? This is also maximum, but ये maximum कौन सी? As per formula, right? So actual value of stress is far higher than the that you calculate from the formula. So that is why maximum stress, which is this, to the nominal stress. So you should have clear understanding. अगर वो twist कर दिया उसने यहाँ पर, if he gives you a twist and if you don't have clear understanding, then you will be in trouble. But अगर उसने copy paste मारा तब तो आप आंसर कर ही दोगे. Okay, let's go to the next one. Pitch diameter for an external or internal screw thread is what? Straightforward है, largest, nominal and mean and all that. So we call it as a effective diameter also. Terminology अगर आपको पता है तो threads में you may be having the idea. So pitch diameter जो है वो that is the example isometric threads में आपका बिल्कुल middle में आता है वो. So you are having this one. So this is the pitch diameter. So इसको हम effective diameter भी बोल देते हैं. So this of the threads, चाहे internal हो चाहे external हो, we call it as a effective diameter also. So B is going to the correct option. Which one of the following is the criterion in design of hydrodynamic journal bearings? Give me. So see, Sommerfeld number is the parameter. Sommerfeld number जिसको हम कैसे लिखते हैं? Zn by P into R by C square. Have you seen this term somewhere? I think we discussed somewhere. So this is basically, these are all the parameters which are in the hand or control of the designer. And all the graphs that you may have, I don't know how much idea you are having. On one axis we are having Sommerfeld number, and on the other axis you are having different dimensional less number which are plotted by Raimondi and Boyd. So those charts are used, right? But anyway, that is the significant parameter which are used. And anyway, I had told you, as per the Petrov, friction coefficient of friction was this one, 2 pi square Zn by P into R by C. मिलता जुलता है. So अगर Sommerfeld number, if you have remembered, coefficient of friction as per Petrov equation, वो आपको easily याद हो जाए, because ये term और ये appear हो ही नहीं है, ये भी appear हो रहा है, ये भी appear हो रहा है. फर्क यहाँ पर square है और यहाँ here you don't have 2 pi square. That's all. Otherwise, when you will try to interpret Sommerfeld number and coefficient of friction in terms of these variables, almost यहाँ थोड़ा सा फर्क आएगा because square में है value, but you should have clear idea about it. So easy to remember. Isolation में मत देखो कि coefficient of friction, because terms more or less same ही appear है. Coefficient of friction, sorry, this is clearance ratio, R by C का उसका square है. This is bearing characteristic, clearance ratio. Okay. Go to this one. What it says, that the stress concentration in machine component of ductile material is not so harmful as it is compared to brittle materials. Now, see, let us say what happens is, this is a ductile material and we are applying load. But keep it in mind, this situation is valid only in case of static loads, which he has not given very clearly. But मतलब उसका यही है. So in this case, in static loads, ductile and brittle materials behave in different ways for the effects of stress concentration. In ductile materials, जैसे हमने लास्ट में stress concentration factor की बात की, you're going to have a very high stress concentration over here. So because brittle material, ductile materials can yield locally. जैसे stress बढ़ेगी, यहां पर यील्डिंग हो जाएगी उसकी डक्टाइल मटेरियल्स की. सो द डिसकंटिन्यूटी विच इज शार्प विल नॉट रिमेन शार्प. तो धीरे धीरे क्या हो जाएगी ये ब्लंट काइंड ऑफ विल नॉट रिमेन दैट शार्प. सो इसका मतलब है बिकॉज ऑफ दिस stress redistribution will take place, and therefore the effect of stress concentration which we have thought of, like the stress will increase to a very large value, that will vanish. Why? Because now this discontinuity has not remained sharp, and the stress concentration will not be there. Initially it will be there, but since yielding will take place locally, so that effect will be negated. So that is why we don't use the stress concentration factors for ductile materials in static loading. In static loading, डायनेमिक में तो यूज करते ही करते हैं. डायनेमिक में whether it is a ductile material or brittle material, we use stress concentration over there. But in static loading, for ductile materials, because of this behavior, we don't use the stress concentration factor. Whereas for brittle materials we use, because वहां पर yielding नहीं होगी static loading में. So that is why in ductile material local yielding may distribute stress concentration, and therefore we don't use the stress concentration factor in ductile material, whereas in case of brittle material we will use. Have a look over here. What he says, bolts in rigid flange couplings connecting to shaft transmitting power are subjected to. Again, सोचना है इसमें थोड़ा सा. If you can recall it, see it properly, then I think so rigid flange coupling, so used to transmit power from one shaft to another. Here you are having flange, and on side view, if you'll see, you are having this flange this way, and you are having bolts which you have used at the periphery over here. Now, if I ask you, if this shaft you have to transmit power from this shaft to this shaft, it is getting transmitted through this, then what kind of stresses are getting developed? Obviously, it's a two flanges and power getting transmitted, right? Completely in shear, torsional shear stress, indirect shear stress. So you're rotating this flange, and since you are having on the periphery those bolts, so obviously it will try to shear the cross-sectional area of all those bolts, right? So it means only torsional shear stresses will be over there, right? No bending. Obviously crushing is also not going to be, because okay, crushing will be there, but okay, you can say that you're having significant area over here. So that is how the situation is going to be. Pure shear case, but shear, torsional shear stress. Okay, what is the basic load rating? Basic load rating is nothing but the dynamic load carrying capacity on the bearing. Basic load rating, alternate name is dynamic load carrying capacity of the bearing. So how this over here, simply he has given you the definition. So dynamic load carrying capacity of a bearing is the load, radial load, that 90% of the bearing in a group can carry for 1 million revolution before the evidence of first fatigue crack, right? So ऐसा लोड बोलता है कि फॉर एग्जांपल अगर let us say if I say that this is one bearing, उसके ऊपर मैं लोड अप्लाई कर रहा हूं. So first I applied a load, let's say 20 kilonewton load अप्लाई किया. So at 20 kilonewton, so it can give the life, 90% of these bearings will give me a life of, let us say 50 million revolution. Hypothetically लिख दिया मैंने. When I will apply a 20 kilonewton load, 90% of these bearing will give me a life of, rating life of 50 million revolution. मतलब क्रैक जो आएगा, that is after 50 million revolution आएगा कम से कम, उससे ऊपर तो हो ही सकता है, because rating life we have seen already. Let us say if I increase the load, if I will increase the load to, let us say, 40 kilonewton, what do you think? The rating life, that is the 90% of the bearings will carry before the appearance first fatigue crack, क्या वो ज्यादा देगा या कम देगा? लाइफ कम होगी या ज्यादा होगी? Is this life going to increase or decrease? क्रैक जल्दी आएगा, बाद में आएगा? Obviously जब लोड बढ़ा दिया तो obviously क्या होगा? The number of revolution at which the crack will get generated, that will get reduced. So it means life may get reduced. तो hypothetically मैंने बोल दिया, let us say 20 million revolution. So the rating life, that rating life was 90% of the bearings. Always we are talking about the 90% of bearings. यहाँ भी 90% bearing, 20 million revolution. अब ऐसी सिचुएशन ले आता हूं मैं where if I apply a load such that, let us say मैंने इसको जो है 100 kilonewton कर दिया, and when I applied a 100 kilonewton, 90% of the bearings have a life of 1 million revolution. Obviously घटेगी, कम होगी, लोड बढ़ा दिया तो. So this load, that is 90% of the bearings can carry for a rating life of 1 million revolution. And 90% of bearings will have a life either 1 million or it will exceed 1 million. That is the meaning of this. तो यहां पर क्या बोल रहा है? Radial load, ये which 90% of the group of apparently identical bearing will run for 1 million revolution. 1 million revolution before the first evidence of fatigue crack. Obviously ये failure है. तो बोलता है ऐसा लोड जो ये bearing carrying 90% of bearings carry कर सकती हैं to give a life of 1 million revolution before the appearance of first fatigue crack. ये मतलब हुआ इसका. तो ये डेफिनेशन है और कुछ नहीं. Let's go to the next one. See this one now. For the break shown in the figure, which one of the following is true? सेल्फ एनर्जाइजिंग क्लॉकवाइज रोटेशन. अब इसमें आपने पता करना है कि ये सेल्फ एनर्जाइजिंग किस केस में होगी. इन विच केस इट इज गोइंग टू बी सेल्फ एनर्जाइजिंग, दैट यू हैव टू इन्वेस्टिगेट. So randomly you can start from anyway. Let's say if I rotate it clockwise, let's see if I rotate it clockwise, so on the shoe the direction of friction force is this way, normal force will be this way. For to verify whether it is a self energizing or not, I need to see whether where is the hinge is down there, and what is the movement. So I think it is the same case that we discussed. I had taken example over here. If you see the movement produced by this frictional force is in the same direction which this force, actuating force, is giving. The actuating force is also giving clockwise. Frictional force is also giving the clockwise about the hinge. It means for this clockwise rotation only, it will become self-energizing for the clockwise rotation of the drum. So my job is done. Whereas it will not be self-energizing if I will give the anti-clockwise rotation. Okay. Now this is a factual information. If you know it, right? So go ahead with this. British Standard Whitworth, BSW का मतलब था British Standard Whitworth threads have angle equal to what? अब ये factual information है. I have taken it. Just remember this information. The Whitworth threads, British Whitworth, जो standard Whitworth threads हैं, they have an included angle of 55 degree. Okay, so just simply remember it. That's all. So which one of the following is a trapezoidal thread? See, trapezoidal threads have a thread angle of 30 degree. That you may be knowing. Included angle between the thread for trapezoidal, I think, is this 30 degree. Your thread angle है, that is the 30 degree. And basically, जो Acme threads हैं, they are the special case of trapezoidal threads because they have a thread angle of 29 degree. Square thread, you know, thread angle is 0. Right? So Acme threads are nothing but the trapezoidal threads only, but with a thread angle of 29 degree. Go through this. Which one of the following types of riveted joint free from bending stresses? Now you have to see the configuration. कौन सा इनमें से ज्वाइंट जो है वो दैट इज फ्री फ्रॉम बेंडिंग स्ट्रेसेस? Just try to apply your thinking. Which one of these is free from bending stresses? There will be no bending. मतलब kind of they will not fail in bending even if it acts. अब मैं क्या कर रहा हूं आपको, आई एम शोइंग द फिगर, आंसर इज विद यू ओनली. ये फिगर है. लाइन ऑफ एक्शन इज नॉट सेम. लैप ज्वाइंट में यू डोंट हैव लाइन ऑफ एक्शन, सेम लाइन ऑफ एक्शन. बट ज्वाइंट में है. लाइन ऑफ एक्शन is not same in case of lap joint. When you don't have same line of action, obviously eccentricity will be there, so bending movement will be produced. And therefore it will try to bend. तो lap joint तो हो नहीं सकता. Then there is another case called as single strap butt joint. Here you have only single strap. So here line of action, even though line of action is same, no, but let us say, so it will not produce movement, but even let us say during installation or something, there is a small error because it can carry heavy loads compared to this one. So if even it's a small error, it may have some possibility of like bending this. So it means it can also bend. And if you want to avoid its bending also, एक और strap पीछे नीचे लगा लो यहाँ पर. So this cannot go up and down. So highest stiffness will be obtained in case of double strap butt joint. So butt joint with double cover will be free from bending stresses. It's on the similar line. Question is tearing efficiency of a double riveted lap joint. Double riveted lap joint having a pitch. See, in case of tearing, you consider the failure at a section, right? So whether it is a double riveted or single riveted, so since you consider it failure at a section, so obviously this is a tearing efficiency he is talking about. We have already discussed tearing strength divided by strength of the unriveted solid plate on per pitch length basis, and there we obtain this over there, where we calculated D by P ratio over there. So this we will obtain, and then efficiency he has okay, he's asking us to calculate efficiency. So over here I have to simply 1 minus 18 divided by 60, so 10, so it becomes 1 minus 0.3, so this 1.7, 70%. I'm not again writing the same thing because similar kind of question we have already done. So it means the efficiency of this joint is going to be 70%. Okay. Okay, just have a look over here. Endurance limit of a component increases as the surface roughness increases, decreases surface roughness on initial increases and all that. So how you have to relate with the surface roughness? See, surface roughness is nothing but these are the peaks and valleys on the surface, minute peaks and valleys on the surface. So it means they are the irregularities on the surface. So if more rough the surface, more stress concentration is going to take place, and therefore more possibility of fatigue failure. When the fatigue load will act, so it can easily fail in fatigue. So it means endurance strength will decrease. That ability to carry the large amplitude of stress will decrease because already a lot of stress concentration has taken place over there, right? So that is why endurance limit is not basically, this is since these are the discontinuities, and there, as we have seen, that discontinuities are going to reduce the endurance limit. Okay, so decrease endurance limit of a component decrease as the surface roughness increase. So for us, surface roughness are the discontinuities. गो अहेड, सी दिस वन। इसको थोड़ा सोच के सॉल्व करना, अगर कंसेप्ट है तो हो जाएगा, otherwise you cannot solve, you will not be able to answer it. If your concept is good, you will be able to answer. If not, then you will have difficulty answering this question. Okay, let us say मैं एक एग्जांपल लेता हूं. This is the case of this. Now keep it in mind, over here we are going to tighten the nut. मैंने नट को टाइट किया, और नट को टाइट करने के बाद obviously when you tighten the nut, what happened? These two plates will be compressed. So let us say I tighten the nut by an amount so that it is equal to, by an amount equal to, let us say 100 Newton. So what happened is, यहां पर ये they are getting compressed by 100 Newton. What? मैंने इतने टाइटली कंप्रेस किया कि यहां पर 100 न्यूटन. So if there is a 100 Newton, obviously क्या होगा? Bolt will also be stretched by the same amount. So ultimately this nut is on the bolt, and when it is tightening the nut, bolt will be stretched through the threads. So it will be compressed, these parts will be compressed, whereas bolt will be pulled by what amount? 100. ये सिचुएशन एग्जिस्ट करेगी किस केस में? When you have simply tightened the nut, you have not applied any external load. अब क्या कर रहा हूं मैं? एक्सटर्नल लोड लगा रहा हूं. Let us say separating force P, external load. So यहां पर मैं एज्यूम कर सकता हूं जो N बता रहा है ना, ये टाइटनिंग फोर्स, ये N है, वो ये N है. So P is I'm applying. Now see what happens is, since he's saying that these plates are rigid, ultimately this load will go from here to this nut only when these plates will deform. जब तक प्लेट्स आपकी डिफॉर्म नहीं होंगी तब तक लोड यहां से यहां नहीं जाएगा. दैट मींस दिस पोर्शन, दिस थिकनेस शुड इंक्रीज. इनडायरेक्टली ऐसे बोल सकते हो, द थिकनेस ऑफ द प्लेट शुड इंक्रीज only then this face of the plate will exert force on the nut, and the nut will move, you will push the nut downward. But since the plates are rigid का मतलब है कि they will not deform. So if they will not deform, तो इसका मतलब ये है कि लोड, जो भी लोड आप अप्लाई कर रहे हो, any load which is lesser than 100 Newton, if I am applying 90 Newton, whatever load, let's say I applied 60 Newton external load, this load will not go, not even a single Newton of this load will go into the nut. अगर नट पे नहीं जाएगा, बोल्ट के ऊपर भी नहीं जाएगा. तो in bolt you are having only 100 Newton which is acting. So if I will apply 60 Newton, this no amount of this external load is going to in the bolt. Then where this load is going? This load is going only to release the compression over there. चल 100 है तो अब क्या हुआ? जब 60 लग रहा है तो it is only releasing. So how much compression is left over here? Only 40. 40 compression is left. That's all. Now let us say if I increase it to 90. So if I increase it to 90, then again this will not transfer to this. Why? Because they are rigid, and therefore where this load is going, it is only going to release it. So if I say if 90 is you are applying as a separating force, over here 100 is compression. So how much compression is left? 100. So it means if I will apply any load lesser than the tightening load, that is 100, then no load will be, external load will be transferred to the bolt, and in the bolt that initial load will remain. तो इस केस में यही पूछ रहा है. Two rigid plates, important यहां पर है rigid plates. Two rigid plates are clamped by means of bolt and nut with initial force N जो आपका 100 है. After tightening a separating force, टाइट करने के बाद, टाइटनिंग के कारण ये 100, because of this tightening, this 100 Newton force came. This force P मतलब मैं क्या कर रहा हूँ, 100 से कम अप्लाई कर रहा हूँ, applying less than 100, is applied to the lower plate. Obviously, whether you apply lower or upper, which in turn acts on the nut. The tension in the bolt after this is, bolt के ऊपर कितनी टेंशन है? Bolt के ऊपर, bolt is going to have only that much tension which was initially present, because no amount is going to be transferred. Let us say, so this answer is very clear now. कितना होगा? N. It will remain N. It will not change. It will remain as it is. फर्क पड़ेगा तो compression में. If there is any difference, that is going to be in the compression over there. Now what happens if it is more than 100? Then it will be transferred. So let us say अगर मैंने किया यहाँ पर, I am applying 102. So what will happen? Out of this 100 will go on releasing this compression. तो 100 तो आपने इसमें से यूज कर दिया उसको सेपरेट करने में. Once they are separated, so whatever additional that you are applying, वो कहां गया? That will go on this face. So इसका मतलब ये हुआ कि additional 2 जो था, 100 went into releasing this compression, making it 0. 100 minus 100 0, and you left out with 2. Now 2 will directly go to this nut, and therefore through nut into the bolt. So it will be 100 plus additional 2, 102. So in that case, in the same rigid plates, if you are applying more than that, then total load will be acting on this will be initial tension plus additional that you are applying over there. Or simply you can say whatever you have applied, if it is 102, on this 102 will be acting. If it is 200, 200 will be acting. So that is how you have. So I think I have given you a brief idea how this problem has to be tackled. D is going to be. Go to this one. Which of the following is self-aligning bearing? Which of the following is self-aligning bearing? Now, see, self-aligning के लिए conical, rectangular. So see, self-aligning का मतलब है कि bearing can adjust itself because of the misalignments. जो shaft की misalignments हैं, because of the alignments that shaft has to go. Let's say small amount of that movement of the axis. So if it should be able to adjust that. That is possible when you will make it something outer race of something this shape. This is fixed inside on the shaft over here, and so that these balls can move on this particular face. So it will be either a spherical ball, you can say. So basically you have to keep it like a spherical ball or spherical roller bearing, right? So it is not conical or that way, that will not give. So it is a self-aligning bearing is either ball bearing or spherical roller. There is one more roller also. Instead of this roller, you can have this kind of roller also. So either spherical roller, if at all roller we are using, this way, spherical roller. So over this roller can go over there, or spherical ball. These are the only options. So here, spherical mean spherical balls भी हो सकते हैं, spherical roller भी हो सकता है. Roller मतलब you are having a cylinder, but cylindrical you are having a kind of this spherical shape. Okay, so ध्यान रहे self aligning. Important क्या है? That movement should be made possible. ये उसके ऊपर जाएगा तभी आपका जो है उसको adjust कर पाएगा. You will be able to adjust that misalignment self. That it will be able to align itself with the axis of the this tapered cylindrical taper. पर वो that will not be able to adjust. Cylindrical taper है तो it will not be able to adjust because वो रेस बनाना ही हमारे लिए मुश्किल है. It's very difficult for us to adjust that. Now let's see this one. Which of the following is suitable for fluctuating demands? Now see, this question is on the similar like previous one. Basically, fluctuating does not mean the load is fluctuating. Here, the fluctuating does not mean load is fluctuating. Keep it in mind. Fluctuating mean again जो है वो थोड़े बहुत fluctuations हो रही हैं वो shaft में. That is the meaning of this. Which of the following bearing is suitable for fluctuating demands? Fluctuating demands does not mean the fluctuating load. He is not talking about a fluctuating load. Fluctuating, what could be the fluctuation? Fluctuation could be through this shaft axis, where you need to align that shaft axis, right? So this fluctuation, which one will be able to adjust? Needle, tapered, and cylindrical. they will not be able to adjust. I have already given you the example. So जो ball bearing basically है वो क्या है? You need to have that kind of race where that shaft when wobbles, then it should be able to move on that. So out of all these, only ball bearings are suitable. Needle or cylindrical, needle and cylindrical both are same thing. Only thing is this is having a smaller diameter. That's all. Tapered, you will not be able to adjust because tapered, it's a conical shape. Tapered roller. So how will you adjust it for this motion? Shaft is over here. Difficult to provide the race. Right? Yes. Needle for space constraint. Needle over cylindrical, why will prefer? Because if I radial space requirement is over there, right? Go for this one. Which of the following is true regarding the fatigue life of a set of identical ball bearing? Just read these statements. Fatigue life क्या है? Simply the life of the bearing. जो life of bearing हम बोल रहे थे, what is life of that bearing? Because when the failure has to take place, will take place through crack, it means it's a fatigue failure. Fatigue means because of those fluctuations in the load, right? So this was what? ये relation था. And since he's talking about the set of identical ball bearings, so one is identical, another one is ball. So if that be the case, you are having set of identical ball bearings. So हमने एक question देखा था somewhere relation, that is L2 by L1, P1 by P2. Raise power because dynamic load carrying capacity same रहेगी, and over there it is going to be K. That's all. So how is the relationship? Which one of the following is true regarding the fatigue life of a set of identical ball bearing? तो fatigue life कैसे होगी? अगर ये bearing है, तो fatigue life is related to the load as in inverse raise power 3 because it's a ball bearing. So inversely proportional to the cube of the load. Load inversely and then cube of that. Same is for this also. With this cube, why? Because it's a ball bearing. So K is 3 for ball bearing. Right? So this is going to be the D is going to the option. Okay, let's see now. So which one of the following statement is in connection with Sommerfeld number is true? Again, so straightforward, I think this is nothing much that you have to think about it. But Sommerfeld number, is what? Your Zn by P R by C square. Now he's talking about in terms of its direct proportional. In terms of load, he's talking about. So load you will get from pressure. And this pressure is the average pressure and that you get from the force divided by, that is the load, divided by projected area of the bearing. This. So if you input this value over here, so obviously it will be inversely proportional. So what is going to be? It is not square off. It is inversely proportional to the load. P will be W by LD. So directly from the formula of Sommerfeld number, you will be able to remember. He may ask you. In exam, he may directly also ask you to calculate the value that bearing you are applying this much load. So how much pressure intensity over there? Simple question could be framed from here as well. Give me this answer. Okay, let's go ahead with this. So fatigue considerations play an important role in the design of all the following components. Which one is true? Go ahead. See, for fatigue, what you need to see? You need to see whether the load is fluctuating or not. Load is varying with time. Load and direction of the load and magnitude of the load is varying with respect to time or not. Bridges. Obviously, कभी कार जा रही है, कभी साइकिल जा रही है, कभी मोटरसाइकिल जा रही है, कभी when you are having this one ट्रक जा रहा है, कभी 100 की स्पीड से है, कभी 10 की स्पीड से है, फ्लक्चुएटिंग, दिस कैन नॉट बी. स्प्रिंग, depending upon the application, will be subjected to. Think of the cylinder valve, जो आपका cylinder valve है, engine cylinder valve है, there you are having a again and again, that is a rocker arm where you have to open that valve and close the valve. There you are having a spring, fluctuating. Then bearings, I have already discussed with you, bearings rotate कर रही हैं, ये भी आपका क्या fluctuating है. Yes, leaf spring also, even leaf spring are getting subjected to fluctuating stresses, right? So you are having gears, they are subjected to fluctuating stresses. फटीग का केस मैंने ऑलरेडी डिस्कस किया आपसे. कीज, की तो केवल आपका स्टैटिक मेंबर है, हब के साथ यू आर परमानेंटली ज्वाइंट, दैट्स ऑल, राइट. सो इट मे बी, सी, सो की जो है, बिकॉज इट इज परमानेंटली ज्वाइंट, बट वी डोंट नो द एप्लीकेशन, बट मोस्टली अगर आप बात करोगे तो की इज द, इन सब में, इन ऑल ऑफ दीज, की इज गोइंग टू बी द काइंड ऑफ द मेंबर जिसको हमने लेस कंसिडरेशन वी कैन पे फ्रॉम द पर्सपेक्टिव ऑफ, बिकॉज उसमें कांस्टेंट लोड लगता रहेगा. मान लिया उसको रोटेशन मिल रही है तो कांस्टेंट लोड उसमें लग रहा है ऑलमोस्ट, ठीक है. सो इफ यू हैव टू सी, हो सकता है पॉसिबिलिटी एग्जिस्ट करे की के लिए भी थोड़ी बहुत, बट इफ आई हैव टू सी, देन द out of all these options, the option which is least you can just think of in terms of whether they will be subjected to fluctuating fatigue loading or not, we can think of keys over there. Okay, I think this was the last question. So I think we covered almost, or not almost, all the 50 questions that we had. 5101. Okay, right. Okay, so I think that is all for today. So I think in the next session also we will be scheduling very soon. So there we will be discussing some more questions from the other area. We will see whether we'll discuss about production, or maybe we are having industrial also. We'll see some of those portions, and we will keep discussing with you. Okay. So see you in the next session. Till then, bye. Thank you. Okay, we'll cover it next session. We'll see it over there.